Earlier on, we came to the conclusion that the way velocities combine, the way speeds combine in relativity, must differ from what we expect based upon Newtonian physics, based upon common experience, right? It's very simple. If you run toward or away from a beam of light with a speed v, you would expect, based upon the usual way that we combine speeds, that the light would approach you at c plus v or c minus v, but that doesn't happen, and therefore we know that speeds must combine according to a different mathematical rule. And in fact, if you remember, I told you that the failure of speeds to combine according to that equation, c plus v or c minus v, is not special to the speed of light. It is indicative of a general new way that speeds combine in relativity. And I gave you a formula for that. So just in a concrete example, imagine that there's a cheetah that runs with speed w, and imagine that you are running away or toward the cheetah at speed v. What will your view be on the speed of the cheetah? It will not be w plus v or w minus v. Instead, we noted that the new formulas look different. They have this funny factor in the denominator. And that funny factor in the denominator is very important because it ensures that if any of the speeds involved are the speed of light, if we are not looking at a cheetah but we're looking at a laser, this velocity combination law ensures that the speed of light will not be increased or decreased if you are running toward it or away from it. So all of that we've already mentioned. What I want to do now is derive this formula for you. All we need is the Lorentz transformation law that we have at hand. So let's make use of it to understand how velocities combine in the special theory of relativity. Okay, so to do that, let's imagine, as in the statement of the problem, that we have, say, this cheetah over here, and this cheetah, say, is running along at some speed w, and imagine that you, who surprisingly look very much like the cheetah, just you're drawn at a slightly different angle, you are running toward or away from the cheetah at a speed v. So in this case, you're chasing after it. So let's do this example over here and work out the velocity combination law for it. The other case will follow just by changing the sign of v. Okay, so what are we going to do? So let's start with platform coordinates. All right, so from the platform perspective, that's us watching this scenario unfold. What would we say? Well, imagine that these guys both start at the origin. So that would mean that at time 0, they're both crossing x equals 0, which means where will the cheetah be at time t? Well, at time t, the cheetah will be at location w times t, just velocity times time. Okay, where will you be? You're running after this cheetah, so let's call that u. Where will you be? Well, you will be at location t, v, t, at time t. Okay, now what I'd like to do is work out from the perspective of you, not the platform, but from your point of view, where is the cheetah in your frame of reference at time t when it's at location w times t? Well, we can work that out. So t prime is equal to gamma times t minus vx over c squared. That's a general formula. But now for x, of course, we can put in w times t. So this is gamma times t minus v over c squared times w t. And from that, we can get half of our problem solved because you know the time at which the cheetah will be at a given location. Now we just got to work out the location from your view. So again, performing the Lorentz transformation from the platform frame to your frame. X prime is equal to gamma times x minus vt. Now x in this case is w times t minus vt. So we have gamma t times w minus v. Okay? So from your perspective, the cheetah will be at location x prime, given by this formula, at time t prime, given by this formula. So from your perspective, running after the cheetah, what will its speed be? Well, we take distance divided by time. So v of the cheetah from your perspective, that's just equal to x prime divided by t prime. And we can just plug in what we have. So it's gamma times t times w minus v from over here, divided by gamma times t minus v over c squared w times t. And what do we have? So the gammas cancel against each other. We've got a t in every term. Those cancel against each other. And what we're left with is w minus v upstairs. And downstairs, we are left with 1 minus vw over c squared. And there you have it. So there is the relativistic velocity combination law. The speed of the cheetah, from your perspective, is not w minus v, which is what Newton would have said, which is what common sense says. Instead, we have the correction factor that we noted earlier, 1 minus vw over c squared. Again, where does that come from? It comes, again, from the Lorentz transformation on time. It comes from the relationship between clocks in the moving frame compared to clocks in the stationary frame. But there you have it, simple derivation showing us this new way of combining velocities. Now we have derived it.